Welcome everyone. Today we have our another new episode on quantum computing. So first I would like to give chance Professor Donald.
Well, um, quantum computing is basically the based on the idea that um, instead of okay, basically the universe is made. We think now of these things called quantum fields. Okay, and so you can have some experience with a field like a magnetic field. So if you look at a magnetic, if you think of a magnetic field, what is it? Is it light? Is it what is it? And what we've come to realize or come to believe is that the universe consists of a of various fields. The main field, one of the main fields, is the Higgs field, which goes through the entire universe and creates mass. And the particles that we have in the universe are are places where there's more energy in these fields, and these particles just pop into existence um, from the energy of these fields. And so that is how we basically think of the quantum level of the universe. So the particles that we're familiar with, electrons and protons and um, neutrons that make up an atom, actually are made up of smaller particles, and there's quite a lot of them. One of the interesting ones are called quarks, and quarks can be up or down, and they also have color. So they which is they don't really have color. We just use color as a way of differentiating them, and then they have interesting names like charmed quarks and strange quarks. And if it's one of those things, it can't be another at the same time. It's one or the other. And as you as you add energy to the quantum fields, there's kind of levels that it pops to. It doesn't go smoothly. It's not continuous like turning a dial on your radio. It's discrete levels that the uh, energy of these fields go to that cause the particles to pop into existence. And those so there's at one level is the lowest level is quantum zero, which in our universe is the lowest possible level of energy. And that's the energy that you'd find between galaxies out in the middle of space where there's nothing. It's cold. It's near absolute zero. It's there's nothing. There's no anything, but there actually is something. There's actually this quantum energy which is everywhere in the universe, and particles are actually popping into existence and coming out of existence even there. So anyway, we are able to look at these basically kind of look at these particles popping into existence and out of existence now. So we're very sure this is happening, or at least by very sure, since we can't really see it, we've developed a theory, and things fit within our theory. So an example of that is we believe that the Higgs field exists everywhere in the universe, and that's the Higgs field is what interacts with other fields to give particles mass, so that particles have mass. And we believe that so much that we spent $10 billion building a particle accelerator at CERN. and we accelerated, and 10,000 scientists worked on this thing. And after years and years and years and years, they accelerated a particle to have enough energy. They accelerated other particles to have enough energy that when they hit each other, it would create enough energy that it would cause the Higgs field to create a particle called the Higgs boson, and it would pop into existence, and we'd be able to see it. And when we did, that's what happened. So when I say that, we're sure that happened, what I'm really saying is that we've made predictions, and those predictions wind up coming true. It's pretty interesting, the idea that these particles, light is doing that too. It's popping in and out of existence, photons. And but anyway, since we can actually detect these things, we can't actually see them, but we can detect them. We're able to start looking at their properties and finding out what they do. And one of the things that we found out, one of the interesting things we found out about them is when we look at them, we change them. And it's simply a factor of, like, if you want to look at a particle, and light, it has mass. So for an instance, if you're looking at it with light, you hit it with light, and the fact that you're hitting it moves it, changes it. And that's called Heisenberg's uncertainty principle. And it's just basically, but you can, so when you ask the kind of questions that you start asking is this particle an up particle or a down particle? Is this particle, what qualities does this particle have based on the kind of particles that I've just been talking about? And the answer is you can't actually really know, but you can guess. And so what you have to do it with enough of them that you can guess, you can make a good guess. So when we're looking at these particles, we're never actually 100% sure what they were doing before we looked at them. But nonetheless, we're sure enough that we can start using the upness or downness and other factors of the particles to be able to use them as if almost like a binary switch. And then the other thing that we use is the discrete energy levels that I was talking about. So what can happen is we can see that if you add energy, it pops up to another energy level or goes down to a lower energy level. And those are things that we can, look at. We can't really see them, but we can find out, we can detect that those things are happening. And so by using that, what we can do is start using that information to in the same way that we use ones and zeros and bits inside of a regular a computer. And this is being done. And one thing that's worth thinking about is that the scale that we're talking about is incredibly much smaller than the scale of a regular transistor, because we're looking at inside an atom. I mean, we are looking at very, very, very small things. So if we were to build a quantum computer, it doesn't take a lot of space or energy necessarily. It actually takes energy to look at it. So the thing of looking at it takes energy, but we could, and it happens incredibly fast. So the theory is if we could get quantum computers to work, we'd be able to have computers that were many orders of magnitude more powerful than our current computers, because we'd be able to be observing this, using the reactions of it, going, asking it to change to different energy states by adding energy, and then observing which energy states it was in. Now, the downside of this is, as I said, we don't always know exactly what's going on. And so quantum computers have been held back by the issue of the fact that it's probabilistic and not necessarily deterministic. That's something that we can work with. There's the math to do that. It's something that's definitely doable, but it is a difficult problem that we're working on right now. And there are quantum computers that have been built, and you can even get access to them at some of the companies and start being able to use them. They call what the individual things qubits, quantum bits, and the one other property that they have is, since there's multiple levels, you can go farther than just ones and zeros. You can have multiple states that you can use in these computers. So the theory is that we'll be able to do the same kind of operations that we've been doing in regular computers, almost thousands of times faster than we can do it, or tens of thousands of times faster than we can do it in our own computers, by using basically the quantum fields that make up at the lowest level of what make our universe There. Thank you.
If you're muted.
Yes, Professor Rao.
Okay, a little hard to parse. Let's start with a correction. The quantum computers and classical computers, at least right now, are probably not going to overlap. Classical computers are really good at certain things: email, spreadsheets, desktop publishing. Those are things they will probably always be better, or at least more efficient at, than quantum computers. Quantum computers are best at solving optimization problems. If you want to figure out the best path for a truck through a city, the best way to schedule 40,000 flights across the United States, that's a quantum computer. What makes quantum computers very different from regular computers is they use quantum mechanics as their core. And instead of ones and zeros, they've got qubits. And as was, I think, partially mentioned earlier, qubits have a superposition, which allows them to not only be ones and zeros, but they can be ones and zeros at the same time. That does require, as a result, a very, very different programming language, a very different approach to programming. A programming element in a quantum computer is called a circuit. And now we've got a number of quantum emulators up where you can learn how to work on quantum computers. And Google has announced they've got a running quantum computer, as has IBM has a running quantum computer, but they have not yet reached quantum supremacy. And quantum supremacy means that the quantum computer has achieved a state where it can outperform a regular computer significantly in anything. So you don't have to have quantum supremacy. You don't have to be better at everything. You have to be better at one thing. And right now, even though we've had announcements, I believe, out of China that, yes, they've achieved it. I believe Google has announced at least once or twice that they've achieved it. I think common knowledge is, we haven't really gotten there yet. But it does represent the future of things like, mapping or understanding outer space, mapping weather patterns on a global scale, and being able to predict things like weather out months, if not years. One of the interesting things I think about quantum computing is some of the unique things it can be used for. encryption is and security is one of the areas that is thought the quantum computer is going to absolutely disrupt. A quantum computer, in theory, can decrypt pretty much anything that has been created using a classical computer in almost instantly. And so you have to protect against that kind of a breach. You have to have some kind of quantum security, and surprise, IBM, which was one of the first companies to attempt to commercialize this stuff, has a solution to address that underlying problem. I'm not aware of anybody else that's come forward with a solution in that area. The other thing is quantum pairs that I find really interesting. The idea of quantum entanglement, where you could have two elements across any distance, and they will react. They will behave the same way. If you move one, the other will move, which could lead to near instantaneous communications across unlimited distances, which could be amazing. But even though that's a capability and a possibility for the future, it's interesting to me that we don't spend a whole lot of time talking about it in the industry. The thing, though, you have to walk away with is that whatever you learned in classical computing will have to be relearned in quantum computing, because the approaches are completely different, and you really have to have a foundation in quantum mechanics as opposed to computer science to make this work. I should say, as opposed to, in addition to computer science, in order to work in this space. The quantum mechanics go to the core of how the computer works, and I'm really not sure you'd be effective as a programmer in the quantum space unless you had an understanding of quantum mechanics. Now, the other interesting thing we could do here, though, is we could use artificial intelligence as a translator, and the idea of having some type of a quantum computing overlay on an AI to handle massive data sets and optimization problems provides perhaps a path to having AIs that are, while not like humans, in fact, would undoubtedly be very different, could outperform humans on a significant scale, and certainly outperform any existing types of artificial intelligences with regard to large-scale problems that require optimization. So the potential here is significant. It will be disruptive. There's absolutely no doubt that once quantum computing becomes real, areas like defense, space exploration, understanding and being able to deal with global warming, even understanding better how the human mind and body works, all become much more probable, and so it will have a massive impact on virtually every aspect of science, just simply because of its ability to consume unheard of amounts of data and relatively quickly come up with deterministic answers and predictions for what that data can do. And quantum computing will be key to making Earth 2 the predictive model that it attempts to be, because the issue right now with predicting out several weeks or even months is and you really need to do that if you want to prevent damage from major weather events, because you need time to prepare. It's right now, you get a warning on a tornado that's minutes long, which is long enough for you to maybe jump into a shelter. But ideally, if you get a warning, a month out or 2 months out, you might be able to do a much better job of protecting the targeted area from the calamity. And with quantum backing and full capture, which is what Earth 2 simulation promises to do, we should have enough data to be able to create predictive models that are accurate at least weeks out and maybe months out with a quantum computer overlay. So the advantages or potential for quantum computing to completely revolutionize science is significant. So it's an amazing area, but just recognize that computer science alone will get you there, at least for now. You need to understand quantum mechanics. It's a very, very different field of study.
Thank you. Professor David J. Kelly, we are discussing about quantum computing. What type of example you want to share from industry?
Well, right now there's only one commercially available quantum computer, and it's pretty specialized, using quantum annealing. I think uh, Don and Rob had some interesting points. I think we're ways away from seeing them kind of commercialized in a consumer sense. Um, but I think where we'll probably see the most, the soonest, most revolutionary implementation of quantum computing will be in encryption, in particular um, quantum encryption, between as a replacement for like SSL. I think Rob touched on that to some degree, and I think that's the most likely, I think, need that'll uh, drive it into the consumer space, and that's for a number of reasons. One, that's something we can actually theoretically do, and there's also just a really pressing commercial need, given that SSL has been hacked and it's becoming easier and easier with each year. And with quantum computing then being available, that just makes it so anyone that can afford the equipment can do it. I think other implementations are probably a ways away in terms of any kind of mass adoption, a long ways away. Like the D-Wave machines, very, very specialized hardware. The more general quantum computers that like IBM is working on, and Google and so forth, they just are not there in a way that is useful, with the exception of maybe certain kinds of statistical analysis and encryption and that sort of thing. I think that quantum computing will be an important leg of what we do in computers, but right now it still is only is minimal impact on what we do in the industry.
Uh, Professor Donald, you know that World Talent Economy Forum, we are actually integrated with more developing nations, especially with the university, with government agencies, and definitely some corporations and banks. Uh, so we are actually developing more research organization, business incubators. Uh, what is your advice if we want to introduce this kind of technology in developing nations? Yes, still they are far more behind, but they can do more research and they can adapt this kind of technology. Today we are actually collaborate with one of the largest universities called Dhaka University. They will introduce World Talent Economy Forum's lab in the university. Perhaps this is one of the biggest university in South Asia, and they have a lot of good researchers. So, what is your advice for our universities?
Well, I want to build on what Rob said. I tried to give a high level idea of some of quantum mechanics, and I like what Richard Feynman said. He says, if you understand quantum mechanics, you don't understand it. I mean, it is a very complicated subject, and to understand it, it's mathematical. You have to understand the math to be able to do it, and the basic math that you need to understand is basically it's linear algebra, except very, very sophisticated linear algebra, where you're talking about working with matrices of tensors. And so in order to be able to understand that, you have to be able to understand tensor calculus, and you have to understand that very, very well. And then they use a special kind of algebras in it called Lie algebras. And so you really be able to understand group theory very, very well. And if you've got that basis of tensor calculus, linear algebra, and group theory, then you can be able to start understanding quantum mechanics. And right now, as David pointed out, the existing machines exist in laboratories with experts who don't accidentally collapse the quantum states by accident, because they're very, very, very sensitive, and you have to exactly know what you're doing to be able to even use them. They don't have I/O in the sense, they don't have memory cards, they don't have I/O in the sense that we're familiar with it. So just getting the data to it now is a big challenge. So as David said, it's unbelievable for, say, and Rob pointed this out, both, for some sorts of statistical models that you just couldn't crunch the numbers in a finite amount of time. And that's what encryption basically is that you permutate the keys. It is one way of doing it, but you've got to just and you find ways of doing it so that to undo it would require so much computational power, or to redo it. So if you just, like, by brute force encode a key with an algorithm and then compare it to an existing key, that computers have gotten so powerful that that's possible to do, and actually find the key by just randomly going through the alphabet and numbers and so on. But if you had a quantum computer to do it, you could do it instantly. And that means that all the existing keys wouldn't be of very much value, because you could just instantly, well, not instantly, but very, very quickly just do brute force attacks. So that's something that is an area, cryptography is an area that is, both David and Rob pointed out, is an important area in it. But really, to understand how they work, you have to understand quantum field theory, and quantum field theory requires, as I said, tensor calculus and understanding tensors very well, and then also matrices, linear algebra, and then also a special kind of algebra, or a special kind of group called Lie groups. And then once you understand that, it's a piece of cake.
Thank you, Professor Rob.
Bustin, we're on the same question. As Ann pointed out, you start with linear algebra. You also want to look at Hilbert spaces and projection matrices as areas of study. But frankly, it's quantum computing, is probably we're demonstrating accidentally, is something that requires a high level of expertise. And if you're going to try to bring it into the school, your first step would be to acquire a leading quantum computer expert to help you formulate the curriculum. The elements around quantum computing are and will remain in high flux until we get to quantum supremacy and lock down on what the best approaches, the most viable methods, and the optimal practices to create a program using quantum computing. One of the elements of quantum computing having to do with security is actually observation, and this is also another area that kind of fascinates me. Is because with quantum computing, if you have a quantum stream, you can tell if somebody else views it. So, for instance, right now, if you were on a telephone call and somebody hacked into the line, the only way you're going to be able to tell if somebody else is on the line, given gone digital some time ago, used to be able to tell because the sound level would drop. But now there's pretty much no way somebody could be listening to you on your phone every time you make a call. You'd never know it. But in a quantum stream, so if you have a quantum encrypted stream, if somebody else observes the stream, not decrypts the stream, simply observes the stream, the recipient would immediately know that the stream had been observed. And so you can imagine in a secure environment, if the United States was receiving quantum encrypted information from a field agent, and Russia was attempting to decrypt that data, so they were observing the data, immediately the U.S. Would know that somebody that other than the agent was observing the data and would be able to respond. Another fascinating area with quantum computing that folks are already exploring, and there have been some successful tests, is quantum teleportation. You know, when I say successful tests, I don't mean that the captain of the Enterprise was beamed down to a planet. Basically, they're just dealing with photons. But they were able to demonstrate that they could send instantaneously using a quantum pair, quantum entanglement, information from one photon to another photon across the Danube. And once again, at least it's theorized that there is no space, no distance limitation for this kind of technology. And if you can send information, who knows what else you could send over time. Certainly, by sending information, you could create clones of things, which of course brings up a lot of the debate of whether teleportation, if we could do it, would in fact be moving you from place to place, or simply be killing you in one place and recreating you in another, which of course has been something that's been explored several times in science fiction, and generally not in the most positive light. But yeah, quantum computing is probably something every major university should at least be spending up on, as long as they've got a focus on a computational focus. I mean, granted, if you've got a school that's focused on animal husbandry, quantum computing isn't going to make a big difference for you for a long time. But if you are a research college, if you are working in computing, if you have a major computing curriculum, computer science curriculum, and you're not looking at quantum computing, you're probably not going to be seen as a major player in the future, or even maybe a competitive player. Because even though quantum computing is probably not going to, at least in their near term, replace conventional computers, but supplement them, who's to say how this is all going to end up? I still remember in the early days of computing, a lot of the leaders saying that the world only really needed 5 or 6 computers. Desktop computers were stupid. The processors that we brought out in the early 90s were so powerful nobody would be able to use what was in them. And right now our smartphones can outperform rather significantly those computers from that time. So perceptions do change, and until quantum computing is real and in production, how it's going to finally emerge is in play, and breakthroughs can happen any place. The schools that computer science programs that have embraced quantum computing will at least be in play for those kinds of changes. The schools that have not embraced quantum computing and have programs focused on training the students will likely find their programs to be obsolete at that time. Because even though quantum computing won't replace regular computing, they will most certainly be enhancing regular computing across a broad spectrum. And those that don't know how to interoperate, don't have a fundamental understanding of how to program, and don't have a skill set that allows them to make the pivot to understanding quantum computing and quantum mechanics, when that pivot occurs, will probably find themselves obsolescent until we can come up with an AI training element or an AI aid that can allow them to bridge the two skill sets. And that'll come, but it probably won't come within the first 5 or 10 years of quantum computing becoming real, because, as I say, it's kind of in flux now. And a lot of those efforts won't even really be started until we have a firm understanding of what works, what doesn't work, and how to do this in a way that can provide that quantum supremacy element that the industry requires to move this into production.
Thank you. This is very, very interesting. Oh, David Kelly, I think he leave already. Professor Donald, what is your concluding remarks for today's sessions, or summary you want to share with our audience? Yeah.
Well, I want to thank Rob for reminding me that when I was thinking about tensors kind of exist within the um, broader idea of topology. And so when he was talking about different kinds of spaces, the key subject to understand there is topology, because you've got to understand things like how space folds over on itself and things like that, which all very, very, very interesting, extremely difficult to understand. um, it's it's something that when you take the courses you're going to spend, it's one of those things that you better just not plan on having that be the part of the thing where you're finding a new mate or uh, you know, going to a lot of concerts or anything like that. It's going to be a time when you're really going to be studying hard. um, I also want to just talk a little, just talk a little bit about what Rob said about quantum entanglement. I think that's a fascinating subject. And basically what it is you take one of these particles like a photon or a quark or something, and you basically split them in half. And the two halves are in a sense, they're in the same place. And so what happens to one happens to the other instantly. Einstein called it spooky action at a distance. And and as Rob's pointed out, they've done it with quite large distances now. They've been able to do that. It's done by like having these like chambers where they manage to kind of isolate a particle in absolute zero, and it's not going to be in your phone anytime soon. And but it's incredibly interesting, and it's teaching us something about how the universe is put together. And we don't completely understand it, but it's but the one difficulty with it is that thing about I said about Heisenberg's uncertainty principle is that it's hard to actually get them to pass information, because we don't know for sure what's going to happen to the particle when we look at it. So unless we know what happened to the particle on one side, we don't know what happened, what it means for the particle on the other side. So it's a little something we're still trying to work out, but we can definitely see that this action is taking place, and it's pretty cool. So anyway, if all those things excite you and start thinking about how the universe works, the math itself, topology, is fascinating. And so it doesn't really matter what, even if you're not planning on building quantum computers or doing quantum computers, it's really important that you have a good, strong program to be able to get this kind of math and into the world. For an instance, one description of artificial intelligence, the layers that you have in a deep learning system, is that they're mapping manifolds. So they map a manifold to another manifold to another manifold, and manifolds are something that's in topology. So learning topology can actually help you learn about deep learning. So there's a lot of overlap between the kind of math that you need to learn for these different things. It's really important. And I also want to leverage off of what Rob said about getting experts there to help you out. Once I was sitting in a pub, it's kind of it's a restaurant in downtown Palo Alto where you could get delicious fish and a beer. And I always wound up talking to whoever was next to me there. And so I really liked it. So I get to talking to this guy, and he's there from Cambridge. And I said, "Oh, what are you doing?" He says, "Well, I'm here consulting to Google on quantum computing." And so we chatted a bit, and he, kind of tried to explain to me what he was doing. But the point I'm making is that even Google searches the world for these experts and pays them handsomely to be able to come and look over what they're doing and try and explain it to them and to the people that work for them. And so I mean, that's the key to having a good university, is having good professors. And so that's what I want to say as my concluding remarks.
Thank you, Professor Rob.
Well, quantum computing right now is predominantly theoretical, not practical. We're working around the edges, but until we get to quantum supremacy, it's largely an exercise in learning and creation, not an exercise in application. That means that, and I'll give you a personal example. I took two courses in calculus when I was in college. And the first one was in theoretical calculus, and it was the only F I got in college because I just couldn't, for whatever reason, couldn't wrap my head around theoretical calculus. And the issue was more that I just didn't find it interesting. And then I took a course in applied calculus, and I had the second highest grade in the class because I found that fascinating. And that's where you're using calculus to solve real world problems. So if you're like me, quantum computing isn't the area you want to go into. Too much theory, too little practice. However, that would flip almost immediately when we get to quantum supremacy, and you can start applying the stuff that you learn immediately to solving problems. Then that would be the area, that would be the time I would enter that particular field, because then it would be doing things I'd be interested in, because I'm a problem solver. I don't want to sit around and speculate about stuff. I want to fix stuff. Just, it's my nature, it's my personality. So if you're like me, quantum computing is probably not an area you want to go into right now. On the other hand, if you love theory, if you love collaborating on concepts and ideas, and you don't really care that much about application, then quantum computing could be a godsend. It's a lot of theory, a lot of discussion, a lot of folks going around and seeing, ooh, can we do with this shit? That's fun for some folks. The other thing is as I mentioned before, you've got to have a foundation in quantum mechanics, and be interested in it. This is not something you go linearly to through computer science. A very different approach to the underlying problem. And so for a computer science specialist doing this right now, you might be wanting to do foundational work to see where the practical applications early on will be, and look at things like how people are bridging traditional computing and quantum computing. But you probably don't need to spend a tremendous amount of time understanding quantum computers yet. You need to understand how to interface with them, but not necessarily how to use them directly yet. It really depends on what your focus is going to be. If it's mostly going to be on research and the wow part of any new technology, then yeah, it could be really cool. If you're mostly focused on wanting to say, well, let's see how we could improve a robot or something along those lines, you're going to be better off in computer science, and particularly if you're looking primarily at things like support jobs. There are no quantum computers out there to really support. And so that's not where you're going to want to be. As far as companies to work with, the two companies that are active and the one country that's very active are Google, IBM. Microsoft does have some efforts in this regard, and they're spinning them up. And the country that's been pushing hard on quantum computing is China. If you've got a close relationship with China, then perhaps working with them would make sense. If you don't, working with any government sponsored entity can be very problematic, particularly if you're looking at the possible outbreak of hostility. So maybe stay away from that one. Google has the tendency to have the attention span of a 4-year-old on sugar, and that means their relationships tend to be very sporadic. The campuses run very much like a college campus, and so it feels very familiar. But the interests and quirks of executive management are and always have been all over the map, and it makes for a very difficult company to work with. IBM and Microsoft are far better. Both have strong and deep relationships with a lot of universities. I would say IBM has the greatest depth in quantum computing right now and the highest interest. But that company is certainly in a space of trying to redefine itself and define and figure out where its future is. They're the ones that actually have demonstrated quantum hardware, and you can rent quantum computers from them. So I think if it were me, I'd start with IBM and then probably fall back on Microsoft if for whatever reason IBM didn't work. But as I say, both companies have relatively robust school programs. Another company that you might think about working with is Intel. Intel hasn't yet really spun up their quantum efforts, but they've started looking at it. And their R&D department is largely connected at the hip to research colleges, and so they've got a lot of practice in form of developing technology in concert with colleges, and they might be interesting because you could come up with them, and they might be more interested in working with schools that don't have much in the way of quantum computing to begin with, where IBM and Microsoft might favor schools. In fact, I would guess they would favor schools that would be able to add to their efforts as opposed to schools that are just learning. But since Intel is just now kind of spinning their efforts up, they might be more interested, particularly with regard to geographic coverage, and working with a university that was remote and spinning up as well. And regardless, you're going to have issues with the companies that are trying to do this, because in many cases, like, they're going to be looking to pull expertise in, not push expertise out. And so if you don't already have a quantum element, it's going to be difficult to get over that threshold. But as I say, look for somebody that may be trying to spin up an effort as opposed to somebody that has a mature effort, because the mature effort folks are clearly going to be looking for knowledge that they don't have and move to, rushing to market, and their priorities are likely to be very different. So that's my basic initial advice. Quantum computing is absolutely a fascinating area, but it just simply isn't practical yet. Outside of security, the IBM actually has rolled a commercial program called Quantum Safe. It's a productized element, and I believe they're the first to productize a quantum element, but the quantum service. But recognize that this particular service isn't yet founded on a quantum supremacy quantum computer, because that thing doesn't exist yet. But it does showcase that we do have at least one practical application, even before we have the computers at the point where we need them to be to move into the mainstream. Final comment: just recognize it. While we've said several times that quantum computing probably will never be on your desktop, we learned one thing in this industry, and that never is a word you should never use. Things change dramatically decade to decade.
Thank you. This is excellent discussion, and especially for our audience, I think it will be very valuable for them. I request all of our audience, please share our content with your government, with corporation and academy. And beside that, tomorrow we have debate. We have debate on universal basic income. So Professor Rob, you will be government side, and Professor Donald, if you want, you can join opposition leader. So
Wait. Just time out. Universal basic income. And so, does the government like it or not like it?
Government like it.
Oh, fine. Government what?
Yes. Yeah, government like it, like universal.
Oh, so I like. Okay, I'm a really strange government. Okay, it could be fun. All right, I'm in.
Okay.
I like it too. I think it's absolutely necessary.
Okay, so Donald's on my team. We'll have to have whoever isn't here needs to be on the opposition side.
Okay. I will discuss with Professor David Smith, but
he didn't show up. He gets what we give him.
Yep.
Okay. Thank you. This is really great discussions, and thank you, everyone. Thank you. Bye-bye, and take care.
Bye.
Bye.